I hope you've had the good fortune of seeing the sky on a clear night, far from city lights, and dark enough for the stars to gleam like gems on black velvet. It's beautiful. And like many great works of art, it invites us to contemplate some big questions. We've known for hundreds of years that all those points of light are distant suns producing vast quantities of light and heat. But are there different kinds of stars? Why are they so bright and hot? Will they keep shining forever? The answers to these questions came only after astronomers learned how to measure the basic properties of stars: luminosity, temperature, mass, and radius. That's our goal in this lecture. We've already learned how to measure a star's luminosity, its total power output. We can use the flux-luminosity relationship. First, we measure the distance to the star, d, maybe with parallax. Then we measure the flux, F, the power per unit area that we detect with our telescope, and then we calculate the luminosity as 4 pi d squared times F. What about the effective temperature, the temperature of the photosphere? We can get that from a spectroscopy. We measure the strength of the absorption lines and place the star on the spectral sequence, which, as we saw last time, is a temperature scale. So that gives us L and T effective. Now, whenever scientists can measure two different things, they feel this urge to plot one against the other. So let's plot L versus T effective. We'll use logarithmic axes as usual. And to get oriented, we'll mark the location of the Sun, which has an effective temperature of about 5,800 Kelvin and a luminosity of 1, that is, 1 solar luminosity. Now let's plot the data for the 1,000 brightest stars in the sky. There's a wide variety, so it's a good thing we used logarithmic axes. The effective temperatures range from around 3,000 to 30,000 Kelvin, and the luminosities range from around 1/3 to 100,000 times the Sun's. The Sun is way below average. It's one of the least luminous stars on the chart. We also see some patterns. A lot of the data points follow a stripe from the lower left to the upper right. The upward slope means that stars with hotter photospheres are more luminous. That makes intuitive sense. But there's also a bunch of points higher up on the left. Those are very luminous stars, but with relatively cool photospheres. What's going on with those? Time for some terminology. The diagonal stripe is called the main sequence. It's kind of a bland name. It was given long before it was understood why most stars fall on that stripe. Meanwhile, the stars on the left are called giants. That name suggests these stars are big, and that much was understood immediately. We can understand it too. The key is that stars are approximately black bodies. Yes, they have absorption lines and other deviations from a pure Planck spectrum, but in broad terms, the black body approximation is okay. So we can use the Stefan-Boltzmann law. The luminosity equals the total surface area, 4 pi r squared, times the black body flux, sigma times T effective to the 4th power. And since we're looking at a logarithmic chart, let's take the log. The result is an equation that connects the location of a point in the chart with the radius of the star. Say we're observing a bunch of stars, and they all have the same radius, r. Then 2 log r would be a constant. So if we plot log L versus log T effective, we would get a straight line with a slope of 4. Here's what such a line looks like on our axes. The entire temperature axis spans a little more than a factor of 10, which means log T spans 1 unit. A line with a slope of 4 rises 4 units in log L as it crosses the chart. Let's return to the data and draw a line with slope 4 that goes through the Sun. so that any star the same size as the Sun, even if it differs from the Sun in temperature, luminosity, mass, age, whatever, will lie somewhere on that line. If we increase r by a factor of 10, log r increases 1 unit, and 2 log r increases by 2. That causes the line to shift upward by 2 units. So all the stars 10 times bigger than the Sun should lie somewhere along this line. Using the same logic, we can draw a line for stars 100 times bigger than the Sun. And now we see why the stars in the upper left are called giants. They are 10 to 100 times bigger than the Sun. We can also see the stars on the main sequence don't all have the same size. Stars at the faint, cool end are the size of the Sun or smaller, and stars on the luminous, hot end are up to 10 times bigger than the Sun. This kind of chart, luminosity versus temperature, is called a Hertzsprung-Russell diagram, or HR diagram, after the astronomers who first drew them in the early 1900s. But their charts were a little different. Following astronomical tradition, they plotted absolute magnitude instead of luminosity. And instead of effective temperatures, which they didn't know at that time, they plotted a color index. So this calls for a little refresher on magnitudes. Remember, the apparent magnitude is a logarithmic measure of the flux, minus 2.5 times the log of flux relative to Vega. The minus sign makes bright stars have low magnitudes, and the 2.5 means that a difference of 5 magnitudes corresponds to a flux ratio of 100. The absolute magnitude is a logarithmic scale for luminosity. It's equal to the apparent magnitude minus 5 times the log of the distance over 10 parsecs. And a color index is the difference between two apparent magnitudes measured through different filters. So it's a logarithmic scale for a flux ratio. For example, the B minus V color index is the apparent magnitude measured through a standard blue filter minus the apparent magnitude measured through a so-called visual filter, which is centered in the middle of the visible range. And since it's all referenced to Vega, the color index of Vega is 0. For the Sun, B minus V happens to be 0.66. The important thing is that the color index is a proxy for the effective temperature. Blue stars are hot, red stars are cool, and the color index is much easier to measure. You don't need spectroscopy. All you need is a pair of colored filters for your camera. A traditional HR diagram shows the absolute V magnitude against B minus V. It has all the same features that we saw earlier, but everything is flipped left to right. That's because a low value of B minus V means the star is relatively bright in B compared to V. It's blue. And a star with high B minus V is red. So that means the horizontal axis goes from blue to red, hot to cool. It's a backwards temperature scale. It's confusing. I really wish that they had originally plotted V minus B instead of B minus V. It would have made my job as a teacher a little easier. But they didn't, and so we're stuck with that tradition. There's another interesting thing I want to show you about HR diagrams. These data points are for the 1,000 brightest stars in the sky. The measurements come from a space telescope called Hipparcos that measured the distances and visual fluxes of about 100,000 stars. But let's do something different. Instead of the brightest stars, let's choose the 1,000 nearest stars in the Hipparcos catalog. This looks very different. There are a lot fewer giants. And the main sequence is still there, but it's much more weighted toward the cooler, less luminous end. Now the Sun looks sort of average. It's certainly not one of the faintest stars. The point of this is that there's a big difference between the nearest stars and the brightest stars. If you pick a certain volume of space and count all the stars inside, what you'll find is that small, faint stars are by far the most common. Bigger and more luminous stars are rare. To find them, you need to look far away. But because they're so luminous, they call attention to themselves. They're overrepresented in any catalog that's based on brightness. That's why Betelgeuse, Arcturus, Aldebaran, and so many other of the famous stars are giants. They dominate our naked eye view of the night sky. In contrast, most of the nearest stars are invisible without a telescope. Within 5 parsecs of the Sun, there are about 80 known stars, of which only 8 are visible to the naked eye. The rest are intrinsically faint. Some of them don't even technically qualify as stars. Those are the brown dwarfs that I mentioned in the first lecture. Let's return to the topic of the day, stellar properties. We've got luminosity, temperature, and now radius. What about mass? If we want to understand stars, we really need to know the mass. Mass determines a star's gravitational pull, its internal pressure, and the amount of fuel that's available to keep shining. So how can we learn a star's mass? Well, to answer this question, we look toward the constellation of Perseus. There's a blue star in Perseus called Algol, an Arabic name that means something like ghoul or demon. It got this demonic reputation because of its mystifying fading events. Every 3 days, Algol drops in flux by 30% and stays that way for 10 hours before going back to normal. You can even tell the difference by eye. Now, today we know there's no ghoul kidnapping the star, but what is going on with Algol? The answer is that Algol is actually a pair of stars that orbit each other and periodically eclipse one another. These pairs of stars, binaries, are very common. About half of the points of light in the night sky actually represent the combined light of more than one star, but our eyes lack the angular resolution to see them separately. Now, most binary stars don't show eclipses. Only a small percentage happen to have their orbits oriented nearly parallel to our line of sight, so that the stars cross directly in front of each other and block each other's light. That's what makes the whole system appear fainter. Eclipsing binaries like Algol are what allow us to measure stellar masses. We'll call on our old friend, Kepler's third law. One way to write it is a cubed equals gm over 4 pi squared times p squared. Now, back in the planetary context, a was the semi-major axis of the planet's orbit, p was the period, and m was the mass of the Sun. But now it's time for me to fess up. When we discussed Kepler's laws, I told a little white lie. I said the Sun sits at one of the focuses of an elliptical orbit. That's not exactly true. The Sun moves too, just a little bit. This follows from Newton's third law. Every reaction is accompanied by an equal and opposite reaction. If the Sun pulls on a planet, the planet must be pulling back on the Sun with equal force. But since acceleration equals force over mass, and the Sun is so much more massive than the planets, the Sun's acceleration is much smaller than the planets, and that's why we often neglect the Sun's motion. But we can't do that when there are 2 stars of comparable mass pulling on each other. We need to solve the two-body problem. What we'll find is that both stars travel in elliptical orbits with a focal point at the center of mass of the system. The center of mass is the average location of all the components of a system weighted by mass. So for 2 stars with vector positions r1 and r2, the center of mass is located at m1 r1 plus m2 r2 divided by the total mass. Now let's solve the two-body problem. We have 2 stars, each of which obeys Newton's second law, F equals ma. So for star 2, m2 times the second time derivative of r2 equals F, which is the gravitational force exerted by star 1. We can write a similar equation for star 1, except this time it's minus F because of Newton's third law. The forces must be equal and opposite. Now let's add these equations. The right side is 0, and the left side can be rewritten as the second derivative of m1r1 plus m2r2. That's proportional to the center of mass vector. So we've just proven that the location of the center of mass doesn't accelerate. The two stars pull each other around, but the center of mass moves in a straight line at a constant speed. That's very simple, and it invites us to make our lives easier and work in a reference frame that moves along with the center of mass. That is, we'll choose the origin of our coordinate system to be located at the center of mass. That way, m1r1 plus m2r2 equals 0. Next, let's go back to the equations of motion, and this time strategically subtract them. We'll multiply the first equation by m1 and the second by m2, and then subtract. What we get is that the product of masses times the second derivative of the relative separation, r2 minus r1, is equal to the total mass times F. Let's use that shorthand, r, for the relative separation. And for F, let's plug in Newton's law of gravity, minus g m1 m2 over r squared times r hat, where r hat is the unit vector in the r direction. The product of the masses cancels out, and we're left with a simple equation. The second derivative of r minus g times the total mass over r squared times r hat. That looks just like the equation of motion for a single mass, which is a huge relief because we already solved the one-body problem back in lectures 4 and 5. The only difference is that what used to be m, the mass of the Sun, is now replaced by the total mass of both bodies. Earlier we proved that this equation leads to Kepler's 3 laws. So, Kepler's laws also apply to binary stars. The first law says that the vector r will trace out an ellipse, although in this case the origin isn't at the Sun, it's at the center of mass. Kepler's second law will also apply, so the relative speed of the stars will rise as they approach each other. And Kepler's third law applies. The only differences are that the m in Kepler's third law is now the total mass of both stars, and the a is the semi-major axis of the relative orbit. That means if we can measure a and p for a binary star system, we can calculate the total mass. That's good progress. But we'd also like to know m1 and m2 individually, not just the total. For that, we use the fact that the center of mass is at the origin, m1r1 plus m2r2 equals 0. That implies r2 is minus m1 over m2 times r1. And since r equals r2 minus r1, we can replace the r1 by r2 minus r, and then solve for r2 again. It leads to m1 over the total mass times r. Now, we already knew the relative separation r traces out an ellipse. Now we see that star 2 itself moves in an ellipse, but it's scaled down by an amount that depends on the mass of star 1. When you do the same thing for star 1, you get a minus m2 over the total mass. The minus sign means star 1 is moving in an ellipse with the exact opposite orientation. So now we can visualize what's going on. Each star moves in an ellipse, and the two ellipses have a common focus, the center of mass. The size of each ellipse is proportional to the other star's mass. So the ratio of semi-major axes, A2 over A1, equals M1 over M2. That makes sense. The heavier body doesn't move as much. And as they move, the stars are always on opposite sides of the center of mass. They also have equal and opposite momenta. We can see that by just taking the derivative of the center of mass equation. That gives m1v1 equals minus m2v2. So their velocities are always in opposite directions, and the ratio of their speeds also tells us the mass ratio. v1 over v2 equals m2 over m1. The heavier star moves more slowly. So to summarize, if we can measure the relative sizes of the orbits or the orbital speeds, then we'll learn the mass ratio. And if we also measure the orbital period, we can use Kepler's third law to learn the total mass. That gives two equations and two unknowns, which is enough information to solve for both m1 and m2. But how do we measure the sizes of the orbits and the orbital period? Well, if our telescope has a good enough angular resolution to see both stars as distinct points of light, we can just track them over the course of at least one full orbit. Some binaries are close enough to do that, but not many. In general, we need to rely on a more indirect method based on spectroscopy, Doppler spectroscopy. Hopefully that word, Doppler, rings a bell. The Doppler effect is the shift in wavelength that you observe whenever the source of the waves is moving. Like when a car is speeding past you, and it sounds like this. The pitch is higher when the car is coming at you, and then lower when it goes away. The sound waves from the approaching car are compressed, and shorter sound waves mean higher pitch. But when this car is speeding away, the waves get stretched out, and longer waves mean lower pitch. Well, the same thing happens when you have a moving source of light. The fractional shift in wavelength is equal to Vr over c, where c is the speed of light, and Vr is the so-called radial velocity, the component of the velocity along the line between the star and us. That's the only component of the velocity that produces a Doppler shift. Now, the traditional word radial here is confusing. It doesn't refer to the radial coordinate measured from the focus of the ellipse, the sense of the word that we've been using until now. Instead, it comes from the concept of the sky as a celestial sphere centered on the Earth. The motion towards or away from the Earth is the radial direction in that spherical coordinate system. When a star is moving away from us, the wavelengths of all its absorption lines get shifted redward. When it's moving toward us, the shift is blueward. So if we can measure that shift, we can calculate the radial velocity. So that's our way in. Even though the two stars of Algol are blended together in the image, the spectrum of that single point of light reveals two different sets of absorption lines, and they're shifted in wavelength with respect to each other because the stars are moving at different speeds. And as the stars go around, we can watch those lines shift back and forth. Let's work out a simple case. We'll assume the orbits are circular, and that on Earth we're viewing them exactly side on. Star 2's orbital speed, v2, is a constant because the orbit is a circle. But the radial component of the velocity oscillates as the star moves away from us, then toward us, and away again. The Doppler shift will vary sinusoidally. If we monitor that Doppler shift for at least one full orbit, we can measure both the amplitude, v2, and the period of that sine wave. Let's put in some numbers. Suppose we monitor the radial velocities of both stars for 100 days. They vary sinusoidally in opposite directions, as we would expect. A full sine wave takes 40 days, so that's the orbital period. And the amplitudes tell us the orbital speeds. It's 30 kilometers per second for star 1 and 60 kilometers per second for star 2. Now let's use these data to figure out the stellar masses. We can determine the mass ratio right away. m1 over m2 equals v2 over v1, which is 2. So star 1 is twice as massive as star 2. Next, we'll use Kepler's third law to figure out the total mass. That means we need both A and P. And we already know P is 40 days. But what is A? A is the separation between the stars. It's the sum of A1 and A2. We can calculate A1 by remembering that over one period, star 1 travels the full circumference of its orbit. So V1 times P has to equal 2 pi A1. Likewise, V2P equals 2 pi A2. Add those together and solve for A, and we get V1 plus V2 times P over 2 pi. That's 90 kilometers per second times 40 days over 2 pi. And when we convert all the units, it comes out to be a third of an AU. Now's the time to use Kepler's third law. We solve for m, and we write it as a scaling relation, just as we did when we found the mass of Sagittarius A star. For P, we insert 40 days, which is 0.11 years, and for A, we insert a third of an AU. That gives a total mass of 3 solar masses. So, we've got 2 stars with masses in a ratio of 2 to 1, and a total of 3. I made the numbers simple enough that we can just do that in our heads. M1 is 2 solar masses, and M2 is 1 solar mass. So that's how we measure stellar masses using eclipsing binaries. We can also make precise measurements of the sizes of the stars by tracking the changes in the brightness during eclipses. In our example, eclipses happen when the stars have 0 radial velocity. That's when they're exactly along the line of sight, moving in the perpendicular direction. Let's zoom in on one of those eclipses. That fading event has 3 parts. First, we see the brightness drop as the disk of star 1 moves onto the disk of star 2. That's the so-called ingress phase. Afterward, the system stays faint while star 2 moves to the other side, and then the egress begins and the brightness goes back to baseline. The durations of these phases of the eclipse teach us the sizes of the stars. Here's how it works. Let's use the symbol tau for the ingress duration, which is also equal to the egress duration. From the chart, tau is 0.18 days. And let's use t for the duration between the midpoints of ingress and egress. That's 0.36 days in the example. During the ingress, star 2 moves a distance equal to its own diameter. So v times tau equals 2r2, where v is the relative velocity of the 2 stars. That's 90 kilometers per second, because star 2 is moving one way at 60 and star 1 is moving the other way at 30. That lets us solve for R2, which comes out to be 1.0 solar radii. So star 2 is the same size as the Sun. How about star 1, the one that's being eclipsed? Over the time interval t, the center of star 2 moves across star 1's diameter. So v times t equals 2r1. Same equation as before, but with t instead of tau. And since t is twice as long as tau, star 1 must be twice as big as star 2. And voila! We got the stellar masses and we got the stellar radii. Now, in real life, the situation is more complicated. We won't be viewing the orbit exactly side-on. The orbit won't be exactly circular, and so forth. So the details will differ, and we would need to fit a more complicated model to the data. But the concept is the same. Astrophysicists adore eclipsing binaries. Even though all we see is a point of light, we can nevertheless measure the masses and the sizes of both stars, sometimes to within a few percent. Eclipsing binaries are like gold. Other types of binaries are nice too, but not quite as useful. They're more like silver or bronze. For example, what about a binary that doesn't show eclipses? In that case, we have no way of knowing the orientation of the orbit. It's tilted away from our line of sight by some unknown angle, theta. And because of that tilt, the radial components of both stars' velocities will be reduced by a factor of cosine theta. Actually, the traditional way to specify an orbit's orientation is with the complement of theta, an angle called the inclination, I. So the radial velocity is v sine I. We can still use Doppler spectroscopy to measure those radial velocities, v1 sine I and v2 sine I, and we can still get the mass ratio by dividing the radial velocity amplitudes, because the sine I factors will cancel out. But because we don't know I, we can't solve for v or a, and therefore we can't apply Kepler's third law. So we can't calculate the total mass. And since there are no eclipses, we can't measure the stellar radii. That's why it's the eclipsing binaries, like Algol, that provide our best data on the sizes and masses of stars, which is crucial information for the theories of how stars work. Let me show you some of those results for stars on the main sequence. We'll start with radius versus mass. And as before, we'll use a logarithmic scale, and we'll use solar units, so the Sun appears at 1, 1. The data show an upwardly rising trend. The more mass of the star, the larger the radius. It's not a straight line relationship. There is a change in slope at about 1.3 solar masses. But it's at least roughly consistent with a line of slope 1, which would imply r is proportional to m to the first power. We saw a preview of this result in the first lecture. If all stars had the same density, ρ, we would expect m to be equal to density times volume, ρ times 4/3 pi r cubed, which would imply r is proportional to the cube root of m. But the data say otherwise, and we conclude that main sequence stars don't all have the same density. How do their densities vary from star to star? In general, density is proportional to m over r cubed. And since we observe main sequence stars to have r proportional to m, their densities vary as m over m cubed, or 1 over m squared. More massive stars are less dense. Now, why would that be? A good theory of stars should be able to explain that. And there's another trend that needs to be explained: luminosity versus mass. That chart too shows a rising relationship. But this one has a steeper slope of about 3. L is proportional to m cubed. Why does the power output of main sequence stars grow so sharply with mass? Soon we'll see how these relationships arise from the basic physics of pressure, gravity, and radiation. But before getting to that, we'll ponder another big question about all those points of light in the sky. Do they have planets orbiting them? That'll be the subject of our next lecture.